Okay, so in this lesson, we will discuss sequences first before we proceed with series. Okay, so we define a sequence as a function, okay, of a function whose domain is a set of positive integers. Okay, so meaning that your sequence, okay, has a domain, okay, of the positive of set of positive integers. So either actually sometimes this is not really just positive integers like 1, 2, 3, 4, and so on. It actually sometimes includes zeros. So although in this case we will consider we will consider only, okay, the domain of your sequence to be the set of positive integers. Okay, so although a sequence is a function, okay, we will not use the common standard function notation for to write a sequence, like for example a of n, okay, where a denotes the term of the sequence. Rather, we will use the subscript notation a sub n instead. Okay, so this is a more traditional and conventional method of representing your sequences. Okay, so for instance, if you have the sequence 1, 2, 3, 4 up to n, okay, we will call a1, or we will map a1. We will map this element 1 into a1, this 2 into a2, this 3 into a3, this 4 into a4, and so on. Okay, so we can actually write your sequence. Okay, we can actually write your sequence in the following manner. So we can write it in this manner that you have an, okay, equals 1, 2, 3, 4 up to n, okay, and so on. Okay, so we call an as the nth term of your sequence, okay, and an enclosed in a curly brace, okay, denotes your entire sequence. So basically, we will use the the notation of enclosing your nth term inside inside the curly brace if we are talking about the entire sequence itself. But if we are talking about just simply the nth term, or the for a particular value of n, that the term that is associated or is mapped onto that term, we will use just simply, or we will simply use the a sub n as the as its notation. Okay, so say for example, we have the following. And also I would also like to emphasize this, that an infinite sequence, or an infinite length sequence, basically length denotes how many terms, the number of terms in a sequence. Okay, so when you say a number of a sequence is infinitely length, when you say that a sequence is infinitely length, it means that it would have infinite number of terms. Okay, and an infinitely length sequence would actually be denoted by an expression of your sequence having 3 dots at the end. Okay, so that means that your sequence is your sequence is non-terminating. Okay, it has an infinite number of terms. But if I actually close out that one, say for example, I just simply say that this is 1, 2, 3, 4, and then dot, and then n. Okay, and then I close it out like this. Okay, this is a finite length sequence. Okay, so this sequence has a finite length, or has a finite number of terms. Namely, there are n terms there. Okay, in this case, there will be n terms. Okay, so I would like to emphasize that that difference. Okay, so here in example 1, we wish to list some of the terms of the following sequences. Okay, so for example, for letter A, we have the entire sequence a sub n equals 3 plus negative 1 raised to n. So what we do here is we replace n with 1, 2, 3, 4, and so on. Okay, so if you actually do that and compute the value of a1, that becomes 3 plus negative 1 raised to 1, which becomes 3 raised to negative 1, so that is 2. a2 equals 3 plus negative 1 square, so this is 3 plus 1, because negative 1 square is positive 1, so this is basically 4. Okay, a3 is 3 plus negative 1 cube, so that should give you again 2. Okay, and so on. Okay, so you'd be able to list down. Okay, you'd be able to deduce the terms of the sequence, which is simply 2, 4, 2, 4. Okay, and it repeats all over. Okay, so that's for letter A. For letter B, your B sub n. Okay, your B sub n is given as n over 1 minus 2 n. Basically, we will use the curly brace. Okay, when we are writing the entire when we are talking about the entire sequence. But if we are just simply saying that bn, okay, that bn is n over 1 minus 2n, it means this is just the n term. Okay, this is just a single number, but this is a set of numbers. Okay, so this again, the difference between this, okay, and this is that this is just a single number, which is the nth term of this sequence. Okay, while here, okay, while this is denotes the entire set of numbers that comprise the elements of b sub n. Okay, so again, as we did with letter A, okay, we'll have we will replace n here equals 1, 2, 3, 4, and so on. Okay, so that we can have b sub 1 equals 1 over 1 minus 2 times 1. So that should give us 1 or minus 2, that's negative 1 half. Okay, b sub 2 is 2 over 1 minus 2 times 2. So that should give you 2 over negative 2/3. Okay. This is not, I don't think this is negative 1. Yeah, the 1 minus 1 minus 2 pala. So this is what, yeah, this is 1. Okay, so let me correct that one. So this is negative 1 there. Okay, so b3 equals 3 over 1 minus 2 times 3. This is negative 3 over 1 minus 6 is 5. Okay, so that's negative 3/5, and so on. Okay, so we can list down the elements as negative 1, negative 2/3, negative 3/5, negative 4 over 7, and so on. Okay, so that's for letter B. So now you can also apply that same rule for letter C. Okay, which simply is a sequence. Okay, that is generated by replacing n with positive integers. That's for letter C. But letter D is different. Letter D is a sequence that is defined using recursion. Okay, we use recursion here. When you say recursion, it means that for you to be able to determine the next term, you need the value of the previous term. Okay, if you want to determine the current term now, okay, the term for a particular value of n. Okay, you need to determine the value of the term before that n. Okay, so here the definition states this way: the terms of the recursively defined sequence dn, where d1 is 25 and dn plus 1 equals dn minus 5. So it means that here we are given that d1 is 25. Now d2, okay, according to this rule, is d1 minus 5. Okay, again, the rule is dn plus 1 equals dn minus 5. So if this is d2, this is d2, if you're talking about n equals 1, okay, if you're talking about n equals 1, so this is d1 and this is d2. So d2 equals d1 minus 5. and D1 is this one. So 25 minus 5, that's 20. So you needed this information, which is your previous term, to determine the present term. The present term we're talking about is this. Okay, the present term is the currently that we are evaluating. Okay, so for n equals 2, again, this is the current term that we are evaluating. So we will have here D2, and this becomes D3. Again, this is dn minus 1, dn plus 1. So this is minus 5, and D2 is 20. Okay, again, using the previous term to generate the next term. Okay, or the present term. So this is 20 minus 5, that's 15. Okay, and again, proceeding, this is n equals 3. So we will have D3 here, which is your dn, minus 5. This is D3 plus 1, this is D4. So your D4 is computed as D3 minus 5. D3 is 15 minus 5, this is 10. Okay, again, using the previous term to compute the present term, or using the previous term of the sequence, okay, to compute the present term of the sequence. Okay, so this is how we do recursion. Okay, this is the process of recursion. Okay, and some of our sequences may be defined using that rule. Okay, there are cases that we will be defining our sequences using that recursive rule. Okay, and you should be able to you should be able to understand what recursion means. Okay, so there. Now, the limit of the sequence. The primary focus of this topic concerns sequences whose terms approaches limiting values. Such sequences are said to converge. Again, when the terms of your sequence approach limiting values, or they tend to have a certain value to which they become equal to as you increase the number of terms. Okay, we say that sequence is converging. Okay, and that value that they are approaching to is that limiting value, or what we call the limit of that sequence. Okay, so say for example you have 1/2, 1/4, 1/8, 1/16, and so on. Okay, as which is this sequence. Okay, as you can see, as you increase your n, okay, so that means that we are in as n approaches infinity. Okay, we say that the limit, okay, of 1 over 2 raised to n as n approaches infinity becomes 0. So it means that as n is increased, okay, say for example we have here n equals 1000. Okay, we can compute for 1 over 2 raised to 1000 as very, very close to 0. And that as you further increase your n, you would see that the terms of your sequence is actually inching closer and closer to 0. Okay, so that 0 is the limiting value and basically the limit of that sequence. Okay, so we formally define that limit here. Okay, so let L, okay, be a real number. The limit of the sequence a sub n is L, written as the limit of a sub n equals L as n approaches infinity. Sorry, the limit of a sub n as n approaches infinity equals L. If for each epsilon, this epsilon is a very small number. Okay, it's a very, very small number approaching 0 also. Okay, so if for every very small positive number, because that very small positive number is greater than 0, so that means that very small number is a positive number. There exists a positive number, another number, okay, such that the difference between the nth term and the limit is less than that very small number. So which means that this emphasizes really that the terms of your sequence is actually not really, or the nth term of your sequence is not actually equal to L, but actually equal to some number, or it is within a certain band of number. Okay, a certain upper and lower limit number. Okay, that is very close to L. And taking into consideration that this number is a very, very small number, actually approaching 0. Okay, so that we take note of the difference of these two, the n term and L, has to be less than that so it means that the n term actually falls within this blue band. Okay, so we consider in this case, if the terms of your sequence, okay, if the terms of your sequence actually converge inside this band, or tend to stay within that band, or within this within this band of numbers, okay, we still consider L to be its limit, okay, and we say that that your sequence actually approaches that limit. Okay, so and n here actually denotes the number of terms. So there is this large M. Okay, there is this very large M that we consider that value of n. Okay, that value of small n. Okay, to be that number of terms which your sequence actually is within this band of numbers. Okay, so in that case, we will consider that your sequence again has a limit L. Okay, and if this hasn't happened, if the terms of your sequence, it does not stay within this very small band of number, then we will say that the limit does not exist, and then the sequence diverges. Okay, so again, if this is the case, your sequence approach a limit L. Okay, it approaches a limit L. Okay, and in that case, we say that that your sequence is converging, or that's the action word for that. We classify that sequence as a convergent sequence. Okay, otherwise, if if L does not exist, or if we can show, okay, if we can show that the terms of your sequence does not stay within a very small band of number, okay, within a very small band of number within L, okay, we said that that the sequence is diverging. Again, diverging is the action word. Diverging, okay, or is said to be divergent. Okay, so these are the terms that we should be able to use, okay, when characterizing our sequence, when we are talking about how it behaves as n approaches infinity. Okay, so these are the possible behavior of the terms of your sequence as your n approaches infinity. It's either converging when we can evaluate a limit L, okay, and it is diverging or divergent when your L does not exist. Okay. Let me just emphasize why why the graph of your sequence is not interconnected. Okay. Again, the domain of your AN are set of positive integers. Okay. Set of positive integers. So therefore, values in between these integers, like for example, the values between 1 and 2, such as, say for example, 0.5, okay, that's not, I mean 1.5, sorry, 0.5 is not between 1 and 2, but rather 1.5 is between 1 and 2. Okay, so this is so 1.5 now. Yeah. So 1.5 is not included in the domain of AN. So therefore, and any other in between 1 and 2, 1.1, 1.0001, and so on. Okay, there's no, those numbers are not included in the domain of A sub n. So therefore, there is no number, or there is no value for A sub n for that. Okay, there is no such thing as A of 1.001. There's no such thing as swap. So therefore, we cannot simply connect these two numbers, these two data points, or these two ANs, this A1 and A2, with a straight line. Because that would imply that there are values between 1 and 2, which is not the case. So that is why you would graphs like this are called discrete, or functions such as this are discrete functions. Okay, they are discrete in their domain. Because they have discrete domain, they tend to have graphs like this. Okay, so I think that was discussed with you with a previous discussion. Okay, so that is how we define now your limit. Now, we read the theorem 1 as follows: let L be a real number and let f be a function of a real number such that the limit of f of x as x approaches infinity equals L. Okay, if a sub n is a sequence such that f of n or f of n equals a n for every positive integer n, then the limit of a sub n equal as n approaches infinity equals L. Here's the thing. What we only studied are the limits for continuous function, such as for example f of x. Okay, where f of x is a continuous function. Okay, excuse my spelling. Continuous functions, no? So continuous function, no? We can only evaluate the limits of continuous function. That's the thing. Okay. So in order for us to evaluate the limit of a discrete function such as a sub n, okay, we need to establish, we need theorem 1 to do that. Okay. So what the theorem 1 states is that if we can establish that the limit of f of x as x approaches infinity equals L, okay, and that if we can actually say, okay, that that the terms of your function, okay, say for example f here is a continuous function, actually corresponds to the terms of your sequence a sub n, at least those on positive integers. Okay, then we can still consider that the limit of your a sub n equals n equal the limit of your a sub n as n approaches infinity equals n. Okay, so that's what the theorem 1 wants us to do. Okay, it basically lays out the groundwork for allowing us to evaluate the limit of discrete functions such as a sub n, okay, by actually comparing it to a function, okay, that is continuous, okay, as long as this equality holds, okay, that the terms of your an actually corresponds to the values of your function at n. Okay, so and anyway, with that being established, we can simply just not really change everything to x first, okay, and then evaluate the limit, and then bring that analysis over our a sub n. We can simply evaluate the limit of a sub n simply, okay, because we have our theorem 1 as our weapon for that. Okay, so here if we find the limit of the sequence whose n term is this one, okay, here's the process kasi dapat. Since a sub n is not continuous, we have to find a function f of x. Okay, that is actually the same as that one. Okay, which is 1 plus f1 over x raised to x, which is a continuous function now. Okay, we consider this to be a continuous function. Now we can find the limit of this. Okay, we can find the limit of f of x as x approaches infinity. Okay, which is the limit of 1 plus 1 over x raised to x as x approaches infinity, which you find in your previous calculus classes, that this limit is actually the number e. Okay, so in that case, if we can, since this this continuous function, okay, at least on n equals 1, 2, 3, 4, and so on, if we actually replace x with these numbers, and that we find that the resulting value f of n are actually our terms of sequence. Okay. Again, this is the keyword here. Okay, or the key sentence here. Okay, if we can establish this, okay, then we can simply say that the limit of a sub n as n approaches 0 is the same as that limit. Okay, the limit of f of x as x approaches 0, which in that case is still e. Okay, but again, you don't really have to go through this rigorous process every time. We can just simply um, jump into this statement. Okay, we can simply evaluate the limit of a sub n as n approaches infinity. That's all there is, because we already have theorem 1 for that. Okay, so yeah. Now, theorem 2 states the properties of limits for sequences a n and b n, which is basically the same properties that you have dealt with in your calculus class before. So here, if you have the sum, or if you're evaluating the limits of the sum of two sequences, okay, you simply add their respective limits. If you have if you're finding the limit of a sequence multiplied by a scaling factor, okay, c, okay, then you can simply just multiply that scale factor to the limit of the sequence. If you're getting the product of uh, the limits of the two, or if you're getting the limits of the product of two sequences, then you can just simply multiply the limits. And if you're getting obtaining the limit of the quotient of two sequences, okay, you can simply divide their limits, provided that the denominators are not 0. Okay, so here we practice some operations on your limits, okay, in which although we have already defined we already have defined these sequences in example 1, if you can remember, and inspecting them from inspecting the limits from these elements, from the elements that we have determined, are actually are fairly easy. Okay, but we can actually use these properties to establish the same assertion. Okay, here, since the sequence is 2 4 2 4, alternate between 2 and 4. Okay, it would it would be obvious that your a sub n would not approach a certain number. Okay, it would not approach a certain number. Okay, it would not get close to a certain number L. Okay, so that we could say that the limit of this does not exist. Okay, this limit, okay, does not exist, and that your sequence diverges. We can actually use this argument also. If we take the limit of a sub n as n approaches 0, I mean n approaches infinity. Okay, that also means we have to evaluate the limit of 3 plus negative 1 raised to n as n approaches infinity. Okay, n approaches infinity. Now, using property theorem 2, property 1, okay, this property, okay, I can write this as the limit of 3 as n approaches infinity plus the limit of negative 1 raised to n as n approaches infinity. Now, this limit is simply 3, okay, since that is a constant number. You're evaluating the limit of a constant number, so that's simply that constant number. But here, you're evaluating the limit of this expression, negative 1 raised to n. And that negative 1 raised to n actually changes values. And that it doesn't, the value it approaches to, okay, depends on whether n is odd or even. Because this, take note that negative 1 raised to n is equal to 1, okay, when n is even, and negative 1 when n is odd. Okay, so there are two values that your function would be equal to, and in that case, having the information that your n is a very large number, which we don't have an information whether that is even or odd, Okay. We can simply evaluate the limit of this. Okay. So we this would actually be the cause why that sequence would this given sequence would actually converge. I mean diverge. Okay. So this very term here. Okay. The oscillatory property of -1 raised to n. Oscillatory means it goes back and forth in the same value. Okay, it becomes -1 and then 1 and then back to -1 again and then 1 and then back to -1 again. So it oscillates between -1. Oscillates. Okay, it is oscillatory. Okay, so in that case, if your sequence tends to be oscillatory, okay, its limit would not exist. So we can simply cannot perform this operation. Okay, so that is why we will say that this limit will not exist. Okay, limit will does not exist, and therefore again our conclusion for that is that your sequence would diverge. Okay, for letter B, okay. For letter B, we can evaluate this limit, okay, by again not going through the whole thing of theorem 1, but simply just jumping through, okay, thinking about theorem 1. Okay, so um, we can since both the numerator and the denominator of polynomials, okay, you can produce if the numerator and the denominator of your of the n term of your sequence is purely polynomial, okay, evaluating the limit as n approaches infinity can be facilitated by producing k over n raised to m terms, okay, because the limit of such terms as n approaches infinity is simply 0. So if you can if you can produce these terms out of your um, out of the terms of your polynomials, both in the numerator and in the denominator, then you can easily evaluate the limit of your function. In this case, if I divide both the numerator by n, okay, if I divide the numerator by n and the denominator by n, I would be able to produce this 1 over n minus 2. Okay, and using both the division and the addition property of your limit, I can actually rewrite this as the limit of 1 as n approaches infinity, okay, divided by the limit of 1 over n as n approaches infinity, okay, minus the limit of 2 as n approaches infinity. This is 1, okay, this is 0, again, the limit of 1 over n raised to k over n raised to m. 1 over n is one example of that. K is 1, m is 1, okay, so the limit of this one is 0. So this is 1 over 0 minus the limit of 2 as n approaches infinity is 2. Okay, so this is negative 1 half. Okay, and if you actually generate the terms of that, so it means that the limit is negative 1 half. So if it means that eventually your sequence, the terms of your sequence will actually become negative 1 half. Okay, if n becomes sufficiently very large. Okay, so there. Next, let us show that the sequence an equals n squared over 2 raised to n minus 1 converges, and if so, let us find the limit of a sub n. Okay. In this case, now in cases like this, okay, in cases like this given, okay, since this is not purely polynomial because we have an exponential term here, another way to actually evaluate the limit of this is by the use of Lyopitos rule. Okay, so the Lyopitos rule allow us to evaluate the limits of expressions, okay, which when you evaluate it, or when you evaluate that limit, becomes one of the indeterminate forms: infinity over infinity, infinity raised to 0, 0 raised to, yeah, 0 raised to 0, okay, and infinity minus infinity. So these are some of your indeterminate forms, okay. So if your expression becomes one of this, okay, when you actually evaluate the limit, okay, then you can use what we call indeterminate forms, okay. We can use Lyopitos rule to do that. And how do we apply Lyopitos rule? Again, if you recall in your calculus, you take the derivative of the numerator, okay. This is especially true if the indeterminate form that we are talking about is this. Okay. So in that case, what we will do is actually one way of this is to first change forms. If you can actually change the forms of this function first, okay. Um, if you can change the form of your function first, then that's the first that's the first line of solution or line of attack that we can use in solving such problems. But in some cases, that would not be sufficient, okay, or that would not suffice, okay. So therefore, we can apply L'Hopital's rule as a last resort, okay. So in this case, um, here we will just simply apply the L'Hopital's rule, although we can apply change of forms here later on. Again, I will be able to show you that, okay. So applying L'Hopital's rule, okay, so we have here we have to take the derivative of n squared, which is simply, okay, 2n. Again, I'm not yet evaluating the limit, so I'm not erasing, or I'm not taking off or taking off the limit operation here, because I'm not yet operating on the limit. I'm just taking the derivatives. And when you take the derivatives, you take the derivatives separately of the numerator and of the denominator, not as a whole fraction. Okay, so here we have the limit as n approaches infinity. Okay, so the derivative of n squared is 2n. Now the derivative of 2 raised to n is you can look at you can look at the derivative tables, but you can work on it this way. If you take if you want to take the derivative of 2 raised to n, let's express it in another way. So let's have 2 raised to n equals, say for example, x. Okay. Now taking the limit of this, taking the limit of this as taking the natural logarithm of this, okay. Taking the natural logarithm of this equation, we will have ln of 2 raised to n equals ln of x, or simply this is n times the natural logarithm of 2 equals the natural logarithm of x. And if you actually apply exponential on both sides, that is, if I actually use this as an exponent of e, and same thing with this one, then I'll have the expression e raised to n times the natural logarithm of 2 equals x, using the properties of logarithm and exponential here. Okay. Now, take note that our original expression is that 2 raised to n equals x. So if I actually take the derivative of this x with respect to n, I'm actually taking the derivative of this with respect to n. Okay, so that's what we're going to do. So we will also take the derivative of this, okay, with respect to n. Okay, so that we will now have the derivative of your x with respect to n as this is e raised to e raised to a constant times n. So the derivative of that, okay, with respect to n is simply k times e raised to kn. Okay, that's the derivative of that with respect to n. So in this case, that constant k is actually ln of 2. So if we continue on, we will have something like this is ln of 2. Okay, this is ln of, or the natural logarithm of 2 times e raised to n times the natural logarithm of 2. But take note that this number, okay, is equal to is simply x, and your x is simply 2 raised to n. Okay, so therefore this number is actually 2 raised to n. So therefore the derivative of your derivative of 2 raised to n, okay, with respect to n is basically ln of 2, or the natural logarithm of 2 times 2 raised to n. Okay, so that's how we get the derivative of your exponential number. Okay, basically there's this simply multiplier. Okay, or there is a scaling factor which is equal to the natural logarithm of the base of the exponential. Okay, so we can now write this as 2 raised to n times the natural logarithm of 2 minus 1. Okay, which still uh, becomes an indeterminate form when you evaluate the limit. You can do that again. You can apply Lyopitos Rule again by evaluating the derivatives of the numerator and the denominator separately. Okay, so you would have something like 2 over again, the derivative of this is we take out ln of 2 or the natural logarithm of 2. Then we take the derivative of 2 raised to n. Again, we have known that the derivative of 2 raised to n is 2 raised to n times the natural logarithm of 2. Okay? And then we don't have minus 1 here already. Okay, because the derivative we take the derivative of this, so that's 0. Okay. So there. Or as n approaches infinity. So basically this becomes the limit, again simplify, this is just simplifying this expression. This is simply 2 over the 2 raised to n times the natural logarithm of 2 squared. Okay, as your n approaches 0. Now here's where we make the argument. Okay. Okay. Since this is not when you evaluate the limit of this is not now an indeterminate form, because this is simply becomes 2 times a very large number. Okay. Very large number. I concluded this is a very large number because if n is a positive number, a very large positive number, then 2 raised to n is a very large positive number. Okay. Just imagine what is 2 raised to 9999, for example. That's a very large number. Okay, and that limit, or the limit of that, okay, as your n approaches infinity, which becomes 2 divided by a very large number, is actually 0. Okay, so here we can clearly see that now the limit of your sequence is actually 0. Okay. Another argument that we can use, okay, to prove that the limit of that number or that expression is 0 is this. So we have we have the limit, or we are evaluating the limit of n squared over 2 raised to n minus 1 as n approaches infinity. Okay. Now, if you cannot make the form k over n raised to m out of this polynomial, remember that in general, n raised to m, b raised to n, okay, is greater than n raised to m, okay, for a given value of b and m. Okay, so in this case, we can argue that 2 raised to n would be greater than n square eventually. Okay, you can actually verify that numerically by saying by making some computations, like for example, for n equals 1, 2 raised to n is 2, okay, and n square is 1, okay. For n equals 2, 2 raised to n is 4, and n square is 4. Okay. For n equals 3, okay, 2 raised to n is 8, and 3 square is 9. Okay. For n equals 4, 2 raised to n is 16, and 4 square is 16. Okay. For n equals 5, 2 raised to 5 is 32. Okay, and n square is 25. For n equals 6, this is what is 2 raised to 6? 64. Okay, and 6 squared is 36. Okay, for n equals 7, 2 raised to n is 128, while 7 squared is 49. Okay, so except for this and this, okay, and this, okay, starting at n equals 5, for n uh, greater than or equal to 5, okay, for n greater than or equal to 5, okay, it is obvious that 2 raised to n would actually be greater than n squared. Here's my conclusion. Okay, here's the conclusion that we can draw out of this. An exponential expression would actually grow faster than a power expression. This is a power expression. Okay, this is a power. Okay, while this is an exponential. So exponentials, okay, grows faster than powers. Okay, so therefore, if you can actually make an expression that is also, say, k over b raised to n, the limit of this, okay, is still, as n approaches infinity, is still 0. Okay, even if, okay, let us do that here. I can actually divide this by 2 raised to n, both the numerator and the denominator. Okay, so the limit of n squared over 2 raised to n, okay, over 1 minus 1 over 2 raised to n as n approaches infinity. Okay, you don't have a problem here because the limit of 1 over 2 raised to n as n approaches infinity is 0. Okay, so this is basically the limit of this is equal to 0. But you may have a question something into this one. Okay, and this is the answer to this. Since the denominator grows faster than the numerator, okay, since 2 raised to n tends to be larger, okay, tends to be larger than n squared for at least at least 5, okay, okay, for n equals 5, for n at least equal to 5, okay, then we can say that the limit of this expression n squared over 2 raised to n as n approaches infinity is still 0, so that this becomes simply 0 over 1 minus 0 or 0. So that's your limit. Again, I did this without using Lyopitos rule. Okay. The use of Lyopitos rule actually is not that popular. It's not that really appealing with, at least with me. Okay, because there are times that the Lyopitos rule will actually force me to look at the derivatives of some functions that are not really known to me. Like for example, this one, 2 raised to n. Okay, so I really have to review first my calculus before I can actually get the derivative of 2 raised to n. Okay, that is why I am always resorting to algebraic means. Okay, so here this shows you an algebraic method of doing this instead of going to the Lyopitos rule. Okay, so again, if you have something like this, remember that exponentials would actually grow faster. Exponentials grow, let's write it here. Exponentials grow faster than powers. Okay. It doesn't matter what their behavior before a certain number. What matters is their behavior as your n grows large. Because that's what we are trying to evaluate here. A very large n. Okay. So it doesn't matter if the pattern is not really that consistent. Okay. For example, in this case, that there is this point actually. Okay. That the exponential is less than the power. Okay. But starting from n equals 5, okay, there is no way that your power can catch up with the growth of your exponential. So therefore, we can conclude that exponentials grow faster than powers. Okay, so that's another way to do that. Okay. Or to evaluate the limit. Okay. So I may have shown you before a way of evaluating your limits using your calculator, but some expressions would not actually allow you to do that. Okay. For example, in this case, you can actually use your calculator to evaluate your limit. So say for example, in this case, we can type in um, x over 1 minus 2x, and then calculate it with a very large n. Say for example, 9999999. Okay. There you can see that your expression would actually lead to negative zero point 0.5. Now, just to be safe, try progressively increasing your x. Okay, by adding more nines. Okay, and see if that becomes consistent. Because the thing is that there are some limits that if you do it this way, do it numerically. Okay, they actually change their final answer when they actually change their answer when you change the value of n, or in this case x. Okay, so in that manner, sequences that are divergent are very susceptible to that kind of behavior. Okay, so you may have an assertion, okay, or you may assert that sequence under that condition is actually divergent if increasing kumbaga, if the limit that you're trying to evaluate here, or if the value that your calculator returns here is not consistent. Okay, it means that your sequence is not approaching a certain limit. Okay, so in that case, you may assert, okay, that your sequence is divergent, but that's not the case really every time. Okay, that's not the general case. You may want to verify it with another way. Okay, but the thing is that if you can find that, for example, you start with 999, okay, and increase it with 9999, okay, you see that your value here is consistent on negative zero point 0.5. Okay, so it is consistent on negative zero point 0.5. So this is a convergent series. Okay, I mean convergent sequence. Okay, and therefore you can say that the limit is negative 0.9. Okay, so but if that is not the case, if you are trying to increase the number of nines, you progressively increase the number of nines, and the values that your calculator returns is not consistent, then there is something behind it. Okay, and one reason is that your sequence is not really convergent. Okay, if you actually try that one here, okay, let's try that one there. We have x squared over 2 raised to x minus 1, and then calculate it for, say, we start with 999. We cannot compute any value. Okay, so there's a problem with with numerically computing your limits with in some cases like this one. Okay, so that is why we really have to resort to analytic means. Okay, you can also use Excel in that in this case. Okay, you can use Excel for that assertion. Okay, say we create a numbers from, say, for example, 1 to 260. Okay, but we know that isn't enough. That isn't enough. But let's just look at the general behavior, and then let's input here the equation, or the expression for the n term expression for your what's that, a sub n, or yeah, a sub n. So this is n squared. This is your n. So let's have this as n squared. Okay, and then let's put it inside the parentheses just to be safe. Although I don't think we need to really put that in parentheses. Then we have 2 raised to n. So again, this is your n. Okay, minus 1. Okay, so there. So we drag it out here so that we can copy the formula. Okay, until we reach 260. Okay, so we see that in this case, your number is getting very, very small. Here, the exponent is already raised to negative 74. This means, this means 3.646878 times 10 raised to negative 74. That's a very small number already. Okay. So that you know, and even if this becomes 70, 70, 70, 71, you know that even if you change your exponent from negative 68 to negative 74, that really makes a very small difference if you're talking about 0. Okay. So here, we can consider that your limit here is actually converging to 0. Okay. So that's how we can, those are the various ways that we can evaluate the limits of your sequences. So here, we have here the analytic way, okay, using the Lyopitos Rule, using algebraic manipulation of your expressions. We can also do it analytically, okay, using your calculator or using your Excel. Okay, so those are the ways that you can actually evaluate limits. Okay, we just define, okay, factorial, because factorial n factorial is something that we will be encountering more and more in later discussions. So here, let n be a positive integer, then n factorial is defined as 1 times 2 times 3 times 4 times until you reach to negative n minus 1. It's n minus 1 times n. Okay, and a special case, 0 factorial equals 1. Okay, so there. Be very careful when you read factorials. 2n factorial is not equal to 2n factorial. Okay, so those are two different expressions. Okay, so be very careful with that. Now let's discuss the theorem 3, squeeze theorem for sequences. Squeeze theorem for sequences is consistent with the squeeze theorem for limits. Okay, if you can remember that you can evaluate limits using squeeze theorem, you can also evaluate the limits of your sequences using the squeeze theorem. And basically, squeeze theorem just simply states that if you can find two sequences, okay, if you can find two sequences that whose limit is the same or equal, okay, and if a third sequence is in between those two sequences, okay, then the limit of the sequence that is in between your first two sequences is still equal to that to the limits of the first two sequence. Okay, so again, you have sequence AN and sequence BN. Okay, now we can if we can verify that both AN and BN have limits L. Okay, and if we can prove that a third sequence CN is in between AN and BN, okay, then we can conclude by squeeze theorem, that the limit of this sequence is equal to the limit of the first two. Okay, that's why it's called a squeeze. Okay, here, you have here two sequences, this one and this one. Okay, so we know if we know that the limit of 1 over 2 raised to n as n approaches infinity is 0. Okay, we also know that the limit of 1 over 2 raised to n as n approaches 0, okay, even if this is negative, this is simply negative of the limit of 1 over 2 raised to n as n approaches 0 by scaling property. Remember the limit of c times L, c times a sub n as n approaches infinity, okay, equals c times the limit of a sub n as n approaches infinity. So ito yung in-apply ko dito. Okay, so since the limit of 1 over 2 raised to n as n approaches infinity is 0, so this is negative of 0 or simply 0. Okay, so those two actually sandwiches this sequence. Okay, you have to prove what you need to prove here is that this sequence is less than this and greater than this. Okay, That is what you need to prove. Okay. Um, we have a, here we have we have a graphical proof. Okay. But um, how to prove it analytically is something that may be maybe something like of a difficult thing for you. Okay. But you can actually prove it numerically. Okay. You can prove it numerically. Okay. So okay. Here we attempted to to generate the first 20 terms of each of the sequence. Remember that this is the sequence that is under test. Okay, so basically this is your AN. Okay, this is your BN, and this is the sequence that we are attempting to prove or to attempting to find the limit of. Okay, so here, that's the sequence that we are attempting to find the limit of. Okay, so again, we find two sequences, this and this. Okay, this sequence, that's your AN, and this sequence, that's your BN. Okay, which we know that both approaches 0. So that when you remember this, when you are applying when you are applying sequence a squeeze theorem, you find sequences that that approach the same limit. Okay, and that would sandwich, or that would be one is less than and one is greater than the sequence under test. This may not be a very easy task for you, okay? But by a lot of practice, you will be able to to master this one, okay? So here we were given, okay, we are already given that these two sequences sandwiches this one, okay. And how do we know that they actually sandwich that they actually sandwich this sequence, or that this sequence is in between this and this? One way is to numerically prove them. Okay, so here I have generated the first 20 the first 20 terms of your AN, okay, and your BN, okay. Now, what I would like to know if CN is actually in between AN and BN. Okay. So here clearly for n equals 1, okay. That is not the case because -1 is less than less than 0.5. Okay. And in this case, okay, 0.5 is greater than 0.25. Okay. And in this case, okay, this -1.667 is less than 0.125. But notice that in this case, starting at n equals 4, this now is in between this and this. Okay, so starting at n equals 4, the terms of Cn are now in between these two. Okay, so you can actually verify that with a graph. Okay, actually that is what is this graph for, but you may not be able to understand it clearly. So let's use an interactive graph here. Okay, which here kasi observe the orange dots. The orange dots actually represent Cn. AN is represented by the blue dots, while BN is represented by the gray dots. Okay, so here's our objective, to see that the orange dot is in between the blue dot and the gray dot. Okay, now here this one at n equals 1, n equals 2, n equals 3, in those terms we find that the terms of Cn, okay, are not in between. Okay, they are not in between this AN and this BN. Okay, for the first 3 terms. But notice that starting at the 4th term here. Okay, starting at the 4th term, your CN is na that is 0.6 okay. That is this one, this value, negative 0.41. This orange dot here. Okay. So you now see that it actually is less than the gray dot, okay, and more than the blue dot. Okay. Now you can see the other details, but if you actually change the scale of your of your chart. Let's say let's make this negative 0.1, okay, and positive 0.1, you will be able to see more details. Okay, here, this is at 4, n equals 4, n equals 5, okay, n equals 6, okay, n equals 7, n equals 8. Okay, and if you want to see more details here, let's still change this because the numbers are getting smaller and smaller. So that the smaller than the maximum and the minimum values in your chart. Okay, so that's why you can see them. Okay, so that is why we need to change. We can change this so that we can see smaller details. Okay, not that detailed. Okay, that. So again, this is 5. Okay, 6, 7, 8, 9, 10. But basically, the general idea is that starting at n equals 4. Okay, your sequence Cn is now in between An and Bn. Now, this requirement, okay, this requirement for theorem 3, okay, for all n greater than or equal to a certain number n. Okay, it doesn't take note, theorem 3 does not require that that your sequence is Cn is between An and Bn for all n. Okay, it requires that your Cn is between An and Bn for at least a certain uppercase n. Okay, in example 5, this n is actually 4, or actually 3. Okay, because 4 is included in the in where it is now sandwiched. Okay, again, this does not require, okay, theorem 3 does not require that your C is sandwiched between A and B for all n. It requires that it is sandwiched between some number or some positive n. Okay, some positive uppercase n. So in this case, that positive uppercase n is actually 3. And here, we can see that for n greater than or equal to 4, okay, or basically, what I was saying earlier was, just to be consistent with the theorem, n is greater than 3, okay. You can say that Cn is sandwiched between A and B. And in that case, theorem 3 applies. Therefore, we can conclude, okay, that the limit of Cn as n approaches infinity equals 0. Okay, even if the first 3 terms are not sandwiched. Again, theorem 3 does not require your Cn to be sandwiched in between A and B for all n. Okay, it only requires that it is sandwiched for most n's. Okay, if it gets sandwiched between A and B, okay, for a certain positive number n, okay, and if you know that An and Bn both approach as the same limit, okay, both approach the same limit, then Cn tends to approach that same limit. Actually, the motivation for and the proof of that can actually be seen from this. As you can see, since both A, okay, and B approach the same limit 0, okay, and since C is to be or the terms of the C tends to be in between them, okay, then obviously C would actually approach that same limit. Okay, so there. Now, in example 5, the sequence Cn has both positive and negative terms. For this sequence, it happens that the sequence of absolute values, okay, also converges to 0. That is, since Cn contains both negative and positive numbers, we call Cn as an alternating sequence. Okay, Cn in example 5 is an alternating sequence because the values alternate between negative and positive numbers. You can see it here, negative, positive, negative, positive, negative, positive, negative, positive. So it's an alternating sequence. If you actually take the absolute value of that, okay, then all of the terms of Cn would be positive. Okay, And it would be it would be interesting also to note that even this sequence would also has a uh, limit of 0 as n approaches infinity. Okay. So in such cases, what the text tells us is that in such cases, it is often convenient to consider the sequence of absolute values and then apply a theorem for. Okay, which states that if the absolute value converges to 0, then the original side sequence also converges to 0. Okay, so which means that if you're having difficulty, okay, if you're having difficulty finding the limit of an alternating sequence, okay, then you can use theorem 4 to find the limit of the absolute value of that sequence. And then by theorem 4, the limit of the absolute value of that sequence also applies to um, the alternating sequence. Okay, so there. Pattern recognition for sequences. Sometimes the terms of a sequence are generated by some rule that does not explicitly identify the end term of the sequence. Okay. In such cases, you may be required to discover a pattern in the sequence and to describe the end term. Okay. Once the end term has been specified, you can investigate the convergence or divergence of the sequence. Okay. So one skill that you need to develop in this particular part of the lecture is to actually make an induction about the end term of the sequence given its terms. Okay. If you have the terms of your sequences, okay. If you have the terms of your sequences, you need to be able to discern a certain pattern, okay, so that you can find the end term. So here in example 6, let us determine or let us find the sequence an whose first 5 terms are this. Okay, so we first start by recognizing the fact that the numerators are powers of 2. Okay, that we can write the numerators as 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, okay, and so on. So we may be able to conclude that the numerator is actually 2 raised to n. Okay. Now the denominator are actually set of odd numbers. Okay, 1, 3, 5, 7, 9. And how do we generate odd numbers? Since we're starting at n equals 1, okay, so that's 1, no? Okay. For n equals 2, so that we can arrive at 3, we need to add 2. Okay, to that. So that's 3. Okay. And then, for n equals 3, okay, to arrive at 5, okay, we need to add, starting from 1, no? Okay, we need to add 4, no? Okay, so that we can have 5. But that means it's 2 times 2. That's 4. Okay. So, and then for us to have 7, for n equals 4, we need to have 1. Okay. I'm fixing this at 1 because basically we want to have the starting term here. Okay. And that I would like to also relate it to the later you would be able to see. Okay, so this is 4, so that becomes 7. This becomes 2 times 3. Sorry. Ito pa rin 2. Then this is 3. Okay, this is 1. Okay. So as you can see, I can write this 2 times 0. Okay. So that should be 1. Okay. So you may be able to see a pattern here. Okay. Here changes with your n. The first column of the number here, or the 0, 1, 2, 3, and 4, changes with n. But not simply changes with n because that is 1 less than the n. Okay. So if we let this to be n, that actually should be n minus 1. Okay. And then this is now consistent with 2 as 2. So we multiply this by 2. Okay, and then this is consistent as 1. So this is 2n minus 1 plus 2 plus 1. Or simplifying this, we will have 2 times n minus 2 plus 1, or 2n minus 1. So that's one way to actually generate your odd numbers. You can actually check that by if n is equal to 1, this is 2 times 1 minus 1. 2 times 1 minus 1. So that should be 2 minus 1, that's 1. This is 2. For n equals 2, 2 times 2 minus 1. This is 4 minus 1, that's 3. Okay, when n is 3, this is 2 times 3 minus 1. So this is 6 minus 1 is 5. Okay, and so on. Okay, so there are actually various ways of generating odd and even numbers. Okay, depending on how you perceive them to be. For example, 2n plus 1 also generates the expression 2n plus 1 also generates odd numbers for positive values of n, but that should include also 0. Okay, for example, if n equals 0, that becomes 2 times 0 plus 1, so this is 1. Okay, for n equals 1, this is 2 times 1 plus 1, so that is 3. Okay, for n equals 2, this is 2 times 2 plus 1, so that is 5. So 2n minus 1 generates a set of odd numbers for n equals 1, 2, 3, 4, and so on, while 2n plus 1 generates a set of odd numbers for n equals 0, 1, 2, 3, 4, and so on. So there are various ways to generate odd numbers, even with even numbers. For example, 2n generates even numbers for n equals 1, 2, 3. Ang ma-generate yung sequence dito is 2, 4, 6, 8, 10, and so on. Okay. But it can also generate the sequence 0, 2, 4, 6, 8, 10, and so on, if you actually have your n equals 0, 1, 2, 3, and so on. Okay, so there are various ways of generating even numbers and odd numbers, but we have to be consistent. Okay, just to be clear here, we have to be consistent. In this case, here I am starting my n with 1. Okay, so I have to generate odd numbers that starts with n equals 1. So I'll choose this I'll choose this expression 2n minus 1. Okay, so that my denominator becomes 2 times 1 minus 1. Here becomes 2 times 2 minus 1. Here becomes 2 times 3 minus 1. 2 times 4 minus 1. You see the consistency. Okay. And then, and so on, 2 times 5 minus 1. Okay. And yeah, this is 32 over 9. Okay. This is 16 over 7. Okay. So, and so on. So the denominator here is actually 2 times n minus 1. So that might be my my n term. Okay. Here. So I can write that an is 2. Okay, 2 raised to n over 2n minus 1. Okay. Now, let's find the limit of an as n approaches infinity. Okay. As n approaches infinity. Clearly, since 2 raised to n rises very fast. Okay. Since 2 raised to n is clearly greater than 2 times n as for some value of n. Okay. We will be able to discern that this 2 raised to n would actually grow faster than this one. And therefore, this becomes very large at some point in time. That the limit of an as n approaches infinity becomes infinite also. Okay. And therefore, the series is considered to be divergent. Okay. So, without a specific rule for generating the terms of a sequence or some knowledge of the context in which the terms of the sequence are obtained, it is not possible. Okay, it is not possible to determine the convergence or divergence of the sequence merely from its several first terms. If you do not know the context by which your sequences are being generated, okay, or if you because there are many patterns that can be discerned out of a certain out of the first few terms of the sequence. Okay, if you can actually take a look at these examples. Okay, this sequence has the same 3 terms. Okay, it has the same 3 terms, and if you only look at the same at the 3 terms of this, okay, and if you don't know where the sequence is coming from, you may be able to the first instinct would actually take you here. Okay, that's the first general rule that you can actually derive. Okay, but if you take a look at some of the other terms, say for example at the fourth term, that actually makes it more make it more varied. Okay, so um, that makes it more varied than 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 the original thinking that we will be able to have. Okay, and here some of the sequences would actually converge, some of them would actually diverge. Okay, for example, we know for a fact that this would converge. Okay, we know that the limit of 1 over 2 raised to n as n approaches infinity is 0. We have already said that this one already. Okay, this one, okay, the limit of 6 over n plus 1 times n square minus n plus 6, okay, as n approaches 0, which can be evaluated this way. You can divide this with you can divide the sequence with 1 over n cubed, because that is the highest power of n in the denominator. Okay, but here's what we're going to do. This is the limit of 6 over n cubed, okay, over this 1 over n cubed. 1 over n actually goes here, and 1 over n squared actually goes here. So I'll actually split this into two factors, okay, as 1 over n times 1 over n squared. This gets to be multiplied on the first factor here. This gets to be multiplied on the second factor. So that becomes 1 plus 1 over n. That's the first factor. And the second factor becomes 1 minus 1 over n plus 6 over n squared. Okay. Now, as n approaches infinity, this becomes 0, this becomes 0, this becomes 0, this becomes 0. So therefore, this is 0 over 1 times 1. So this is 0. So the limit of this sequence is 0, and Bn is convergent. Okay. So you may be able to verify how these sequences can converge. But the main idea here is that given the first few sequences of first few terms of a sequence, and without any idea on on the context behind this behind the sequences, you may be encountering difficulties in finding the general term or the end term of the sequence. Okay, so one way to actually work on this is to be really familiar with how the sequence is generated. When the sequence is from a practical problem, more or less, you know, you will have an idea of the context behind the sequence. Okay, so that's a very powerful way of knowing the end term of a sequence by first knowing the context behind the sequence. Okay, so the process of determining an end term from the pattern observed in the first several terms of a sequence is an example of inductive reasoning. So I have already mentioned this to you before, that in mathematics we use to be able to arrive at an answer, we either use inductive reasoning, okay, or deductive reasoning. If you're starting from the terms going towards the end term, so you have 1/2, 1/4, 1/8, 1/16, and so on, and then you were able to write 1 over 2 raised to n. Okay, you're using inductive reasoning to generate this. Okay, whereas if you have if you're given 1 over 2 raised to n, and if you're able to write 1/2, 1/4, 1/8, 1/16, you're using deductive reasoning for that. Okay, so as I explained earlier, if you're starting from the examples and then you're writing the general rule, or the general rule for that for those, you're using inductive reasoning. Okay. Conversely, or in another way, if you're using the general example, I mean the general pattern or the general concept, okay, and you're asked to generate examples out of that general concept, you're using deduction. to be able to write this. Okay. So here, let us try to determine the end term for the sequence whose first 5 terms are this. Okay. We take note that number 1. Okay. We take note that number 1, your series is alternating. I mean, your sequence is alternating. Okay. So, if your sequence is alternating, it involves the factor -1 raised to n. Okay. Or another factor that is involved here is -1 raised to n plus 1. Okay. What's the difference? This is when your sequence, you use this. Okay. You use this when your sequence, or when the sign of the first term of your sequence is negative, because when n is equal to 1, this is negative. Okay. So if and not just that, if the odd terms are negative, okay, starting with the first term, okay, this factor might be might appear. Okay. Whereas if your odd terms are positive, okay, odd terms are negative here. Okay. If your odd terms are positive, so therefore even numbers are even terms are negative. Starting at n equals 1, because at n equals 1, this is n squared, -1 squared, so that's positive. Okay. So here your even terms becomes negative. Okay. So these two forms might be, these two factors will be useful for alternating sequences, such as this one. So here we see that the if we let this to be a now, so this is a1, a2, a3, a4, a5, okay, and so on. You see that a1 and a3 and a5 are negative, so you have your odd terms to be negative. So more or less this would appear. Okay, so that's one. Number 2, let's look at the numerator. The numerator is 2, 8, 26, 80, 242. You might have a difficult time finding a pattern for that one. Okay, but as you can observe, that number actually grows very large in the first few terms. Okay, it actually grows very large in the first few terms. There are two numbers that would grow very large. Okay. Eventually. Okay. Numbers such as n factorial and 2 raised to n, and an exponential, say b raised to n, would actually grow very large. Okay. But the difference here is that b raised to n grows very large at early stages, but eventually, n factorial would actually grow larger than b raised to n. Okay, factorials tend to grow larger than the exponentials at a later time. Okay, when n is really sufficiently large. Okay, b raised to n grows very large at the start, but tends to grow slower relative to the factorial. Okay, so here, as you can see, 2, 8, 26, 80, and 242 grows very large. Those numbers grows very large. So that may lead you to think that is an exponential. And although I am seeing here that this is 3 raised to n minus 1, I am trying to give you some clues on how 3 raised to n minus 1 might be a possible candidate for this one. Okay, so again, two numbers, n factorial and b raised to n, grows large. Okay. Okay, grows large for increasing n. Okay. For small n, for small values of n, b raised to n tends to be larger than n factorial. But for larger n, I don't know what's the limit. It actually depends on the base. Okay, but generally, at some point in n factorial would actually overtake your exponential. So if you're seeing that your number is growing large, okay, for the first few terms, that might represent an exponential, okay, rather than a factorial. Because here, as you can see, both your numerator and your denominator are growing large, okay, but the numerator grows large here. But remember that this is just the first 5 terms. So since this is just the first 5 terms, your numerator might be an exponential, okay, and your denominator might be a factorial. And one way to actually be sure that your numbers are terms of a factorial is that you should be able to be familiar with the terms of a factorial. Okay. Those terms are the first few terms are 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is, yun, hindi ko na alam. 6 factorial is 120, 720, okay. 6 factorial is 720, 7 factorial is, hindi ko talaga alam to. 720, let's just simply type 7 factorial. Okay, 7 factorial is, ayan, 5040 and so on. Okay. So you should be able to be familiar with this number pattern. Okay, especially when dealing with sequences that may contain factorial. As you can see here, that number 1, 2, 6, 24, and 20, the set of numbers 1, 2, 6, 24, and 120 actually appear on the denominator. So parang mas ina-enforce niya. That enforces your idea that the denominator is a factorial. Okay, and the numerator is an exponential because it grows large. Okay, at least for the first few terms. Okay, so here, but how do we determine if it is exponential? You try out some terms. Say for example, you start with 2 raised to n. Let me rewrite this on that side of the board. Okay, so one of the we already have established some facts regarding this. So number one, this is an alternating sequence with the odd terms being negative. So the negative 1 raised to n factor would appear in our final form. Okay. Number two, that the numerator is a sequence of exponentials. Okay, and number three, that the denominator is denominator is a sequence of factorials. Okay, and plainly factorials talaga siya kasi 1, 2, 6, 24, 120 is simply n factorial. So sigurado tayo that this is n factorial. Now, what we need to decipher now is this numerator. Since this is exponential, you may try 2 raised to n is or 2 raised to 1. If it's 2 raised to n, the term should be 2. I started with 2 raised to n because the first term is 2. Okay, so 2, 4, 8, 16, 32, 64, which after the fifth term is not sufficient to catch up with the with 242. Okay. So this will not really be 2 raised to 2. Let's try 3 raised to n. This is 3, 9, 27, 81. I don't know what's the next what's the next after that. What's 3 raised to I need 3 raised to 5. 3 raised to 5 is 243. Okay. 243, which is close to, actually the terms here are actually 1 less than the terms of the 3 raised to n. So we can say that the numerator is actually 3 raised to n minus 1. Okay, so that completes now our inductive or our induction, in which case we can now write the n term here as negative 1 raised to n for the signs. Okay. Multiply to 3 raised to n minus 1 for the numerator, and then the denominator is n factorial. So that is your n term. Okay. So this is negative 1 raised to n times 3 raised to n minus 1 over n factorial. Okay. So now, the next thing that we will have to do, okay, is to determine the convergence or divergence of the sequence. No? So since this is an alternating sequence, we can start with applying theorem 4. Okay, we can start by applying theorem 4 here. So by applying theorem 4, okay, by applying theorem 4, theorem 4 is the absolute value theorem, which means that the limit of our alternating sequence an as n approaches 0 is actually equal to the limit of the absolute value of that sequence as n approaches 0. So in that case, if we want to evaluate the limit of this, we simply have to evaluate the absolute value of this one. Okay, so in that case, we will have to the absolute value. If you take the absolute value of this sequence, that just simply means you have to remove that a raised to negative 1 raised to n. Okay, if you take the absolute value of this, that simply means you have to remove this because this is the one that generates the sign. Okay, and if you want to make this positive, you just simply remove this from the factor. Okay, so that simply means we simply have to evaluate 3 raised to n minus 1 over n factorial as n approaches infinity. Now here's the trick to this one. Okay, here's the trick to this one. We cannot use derivatives here because we don't know how to get a derivative of a factorial. Okay, and basically this becomes 0 when you get the derivative of this one. So Lyopitos Rule would not work here. Okay, but we can reason out it this way. Okay, again, your numerator is an exponential, your denominator is an exponent, is a factorial. As I said before, factorials tend to grow faster than exponentials as your n grows larger. Okay, exponentials. I'll write it here. I know I already have written it here somewhere. Ito. Okay, but I'll write it here. Exponentials. Factorials pala. Okay, factorials grow faster than exponentials for some value of n. Okay. So earlier, our reasoning was this. When we compared exponential to power, okay, our reasoning was this. Exponentials grow faster than powers. Okay. For some value of n. Okay. So, using this idea, we have established that something like n raised to m over b raised to n would actually approach 0 as n approaches infinity, because the denominator grows faster than the numerator, and in the end, okay, this will have a very large number compared to this one, so therefore that becomes 0. We can use that same argument here, but to write that b raised to n over n factorial actually approaches 0 as n approaches infinity. Sorry, that's 0. Okay. B raised to n over n approaches 0. B raised to n over n factorial approaches 0 as n approaches infinity. Okay. Same argument. Okay, same results. Okay. So here, we can see that the limit of 3 raised to n minus 1, okay, over n factorial as n raised to n. Again, this is an exponential. This is a factorial. Okay. Factorial tends to grow faster than the exponential. So therefore, eventually, this becomes a very large number. Although this is also a very large number, but since this grows faster than this one, then we can say that this limit is 0. Okay, and therefore conclude that the limit of, again, by theorem 4, this is simply the limit of the absolute value now. Okay, but by applying the theorem 4, we can conclude that the limit of an as n approaches infinity is 0. Also for the alternating sequence. Okay, so we have that conclusion here. Okay. So now let's move the discussion to monotonic sequences and bounded sequences. So far, we have determined the convergence of a sequence by finding its limit. Okay. Even if you cannot determine the limit of a particular sequence, okay, it may be still useful to know whether the sequence converges. If it is not possible that that we can find the limit of the sequence, so that to have a say whether that sequence converges or diverges. Okay. We may be able to still determine their convergence or divergence without actually knowing the limit. Okay. But before we do that, we define two terms. Okay. Number one, monotonic sequences. A sequence an is monotonic if the terms are non-decreasing, okay, or if the terms are non-increasing. So either your terms are growing or increasing or decreasing, but not both. Okay, so it's either increasing or decreasing. Okay, so that's a monotonic sequence. Okay, here obviously since your sequence is oscillating between 2 and 4, this is non-monotonic because your terms increase, then decrease, then increase, and so on. So hindi yan monotonic. Okay, again, a sequence is monotonic if um if it is increasing or decreasing exclusively. Okay, here Bn is 2n over 1 plus n. The first 6 terms are this one. Okay, so we find if this sequence is monotonic by trying to know whether the succeeding terms are actually smaller than the previous terms. Okay, you can do that numerically by listing the first terms. Kaya lang, the danger on this is that some sequences kasi might be increasing its terms on the first few terms and then start to decrease afterwards. O kaya baliktad. It actually decreases on the first few terms and then it increases. Okay. Such sequences are also considered monotonic. Okay. But they are monotonic for some value of m. Okay. And later on we will know that in that particular case, we will be able to consider them also as monotonic. Okay. But we determine them analytically. Okay. So how do we do that analytically? So we actually want to compare Bn and Bn plus 1. So Bn is the nth term. Bn plus 1 is the next preceding term. Okay. So if we have Bn as 2n over 1 plus n, then Bn plus 1 is 2 times n plus 1 over 1 plus n plus 1. Let me write it here. So Bn is again 2n over 1 plus n, and Bn plus 1 is 2 times n plus 1 over 1 plus n plus 1. Okay, or this is 2n plus 1 over 2 plus n. Okay, just being consistent with that. Now let us compare them. Okay. Let's find out if 2n over 1 plus n, is it greater than or equal to, okay, 2n plus 1 over 2 plus n. This is assuming that your sequence is decreasing, because I am assuming here that the Bn term, the n term, is larger than its next term. Okay, so how do we proceed? Now let's try to work on this inequality. Okay, by first multiplying this with both sides with 1 plus n and then 2 plus n. Okay, so that the left side of the inequality becomes 2n times 2 plus n, and then the other side becomes 2n plus 1 and then 1 plus n. Okay, now expanding this, we will have 4n plus 2n squared. Okay, and then this one becomes 2, or let's be consistent now. This is 1 plus this is 2 plus 1, so that's 3n, and then plus this is 2n squared. Okay, now but before I proceed, let me just make some corrections kasi that pala this is 2n plus 2. Sorry. Okay, so this is 2n plus 2. So this is also 2n plus 2. Okay, so this is 2n plus 2. 2n plus 2. So this becomes, this is supposed to be 2. Okay, this is supposed to be 2. And this is supposed to be this is 2 plus 2, so this is 4. Okay, this is 4 and this is 2n. Okay, so here if I actually subtract, okay, if I actually subtract 4n minus 2n squared on both sides, okay, subtract 4n minus 2n squared on both sides, this becomes 0, this is 0, this is 0, and this is 0. So this is 0 greater than or equal to 2, which is not true. Okay, but rather this is 0 less than or equal to 2. Okay, this is a more true statement. So instead of actually saying that bn is greater than or equal to bn plus 1, what was true as because of the results of our proof, okay, is actually that your bn is less than or equal to bn plus 1. So which means that if the present term is less than the future term, okay, it means that your terms are increasing. Okay, it means that your terms are increasing. Okay, and it happens in in all cases. Okay, but again, if you will be having difficulty in doing this, you can actually do this numerically. Okay, but just to put a perspective on this, make sure that when you're using numerical proof, okay, you use as many examples as possible. Okay, you use as many examples as possible. Okay, here, so we generate bn as 2n over n plus 1. Okay, this is your n. Okay, while this is 2n plus 1, okay, over 1 plus n plus 1. Okay, so again, your general term or your n term is 2n over 1 plus n. So this would be your bn plus 1. So this is what you can see here in this formula. Okay, again, this and this. Okay, so we try to copy those formulas here. I have the first 35 terms here. Okay, and take a look at the pattern. Okay, is this term generally smaller than this one or generally larger? So as you can see that it is actually larger. Okay, or you can, instead of actually looking this in two columns, you can actually look it here. Simply look at this if this is increasing or decreasing. Okay, if the numbers are increasing, then that sequence is monotonically increasing. Okay, while if it is decreasing, okay, that sequence is monotonically decreasing. Okay, so in this case, it is actually monotonically increasing. Okay, what we do is compare term by term. So here we see that the term are actually increasing. Okay, or actually is the the present term is actually less than its next term. Okay, so there. So we say now that Bn um, is increasing and the sequence is monotonic. Okay, so here's a graph of it to prove that it's actually a monotonically increasing function. Okay, for letter C, I would like to leave this to you as an exercise. Okay, um, but as you can see in the graph, okay, some of the terms, okay, are increasing, but at certain point, actually at n greater than or equal to 2, starting at that, okay, your terms tend to be now decreasing. Okay, now there are there is a there are two schools of thought here. Okay, number one, this sequence is generally not monotonic. Okay, this by definition, this sequence is not monotonic for all n. Okay, but sometimes, okay, sometimes if you put this sequence in analysis, okay, you might try to force the sequence to become a monotonic sequence by actually specifying that it is monotonic for monotonically decreasing for n less than 2, for n greater than or equal to 2. Okay, because from n greater than or equal to 2, the sequence indeed is decreasing. Okay, but this is not a monotonic sequence for all n's. Okay. By definition, we will consider monotonic sequences for all n. Okay. Um, all terms ang pinag-uusapan natin dito. We are talking about all terms here. Okay. So in that case, if you're talking about all terms, then we're talking about all terms. Okay. But there are times, okay, in some analysis, that you may be saying that that sequence is monotonic just for certain values of n. Okay. But here, to answer this question, your sequence is not monotonic because it is increasing from term 1 to term 2. But starting term 2 and onwards, your sequence is now decreasing. So therefore, this is not monotonic. Okay. Next term that we need to define, bounded sequence. A sequence is bounded above. Okay. If there is a real number, such as the upper limit, okay, of your sequence is lower than that upper bound. Okay. Okay. So it means that it is bounded above, while it is bounded below when there is a number n that your sequence is greater than the terms of your or the n term of your sequence is greater than that lower bound. Okay. Now, if there is if m and n are both existing, okay, and both finite, then your sequence is said to be bounded. Okay. So if there is an upper boundary and a lower boundary, okay, then your sequence is said to be bounded. Okay. Now, by theorem 5, a bounded monotonic sequence is convergent. Okay. So if you can identify a sequence that is both bounded and monotonic, and when you say bounded, it has an upper and a lower bound. Hindi sufficient that the sequence has an upper bound only or a lower bound only. Okay, it should be bounded, okay, both in the upper has an upper limit and a lower limit. Okay, so if a sequence is both bounded and monotonic, it is a convergent sequence. By the way, speaking of bounded sequence, okay, all sequences in example 8 are bounded. Okay, for letter A, since the sequence repeats between 2 and 4, 2, 4, 2, 4. Okay, the lower bound there is 2, the upper bound there is 4. So therefore, your sequence is bounded. Okay, for letter B, the lower limit there is put to be 1. Okay, and if you take more a more thorough inspection of your 2 raised to n over 1 plus n. Actually, if you evaluate the limit of 2 raised to n over 1 plus n as n approaches infinity, this is basically the limit of, I'll divide n on both on the numerator and the denominator, so this becomes 2 over 1 over n plus 1 as n approaches infinity. So therefore, this limit is 2. This limit now, okay, is the upper bound of your And since this is the minimum value of your sequence because that's the first term, so your sequence is actually bounded at the upper bound. It has a 2, or it is limited to 2. On the lower bound, it is 1. So there is an upper bound and a lower bound. So therefore, the sequence is bounded. Okay. So, yun. For letter C, okay, for letter C, the upper bound of the sequence is okay. We will not use we will not evaluate the limit of of your n square over 2 raised to n. Okay. To find n approaches infinity, to find the lower bound, to find the upper bound of your sequence. But although we can use this to find the lower bound, which is 0, because eventually we will know that this becomes 0. But its upper bound is actually its maximum value, which is 4/3. So this one. Okay. So now your sequence is said to be bounded between 0 and 4/3. The boundary of your sequence is facilitated. The finding of or the determination of the the upper and the lower bound of your sequence is actually facilitated by finding the maximum and the minimum values in your sequence. Okay. And if your sequence has a lower bound, okay, if your sequence is has a lower or an upper bound, one of them might be its limit. Okay. Because your sequence will tend to approach that. But here's the thing. We will use this theorem 5 for sequences that we don't really have an idea of its limit, because we might have difficulties in evaluating its limit. Okay. So we'll talk about this later on. Okay. So we say that a sequence that is both bounded and monotonic is convergent. Okay. But it doesn't necessarily mean that if your sequence is not monotonic, automatic non-convergent na siya or divergent na siya. Okay. As in for example in this case. Okay. Still that sequence is convergent. Okay. That sequence is convergent. Okay. So we already have determined this already before. Okay. Although the sequence is not monotonic. Okay. We will not be jumping into conclusion by using theorem 5 that to say that sequence Cn is is divergent. Okay. This is convergent. Okay. It is just that not all sequences that are not monotonic are divergent. Okay. Hindi lang siya monotonic kasi. Actually, this is what I've been telling you. This is not monotonic just for the first 2 terms. Okay. But it's actually generally monotonic for n greater than equal to 2. And if you actually ignore this part, okay, you can say that that sequence is monotonic. So therefore, you can still argue that this sequence should be convergent under theorem 5. Okay. So ayun, kasi ganito yun eh. The convergence of the sequence has nothing to do with the behavior of the first 2 terms. Okay, with the first few terms. The convergence of the sequence actually depends on the behavior as it approaches infinity. Okay, so you look at the general behavior, not the behavior of the first few. That is why I am saying earlier that that there is a danger in making your conclusions out of the first few terms. Okay, so there. Now, let's have this. The sequence 1 over n is both bounded. Okay, because its lower limit is 0, found by the limit of lower bound, found by the limit of 1 over n as n approaches infinity, which is 0. Okay, and its upper bound is 1 because the maximum value is obtained when n is equal to 1. So your a1 is 1. So your sequence is between 0 and 1. So it's bounded. Now, generally, 1 over n is decreasing. Okay, if you actually find the behavior of the terms, it's actually decreasing, such as this one. Okay, so it's both bounded and monotonic. So therefore, we say that the sequence 1 over an is convergent. Okay, this one is n squared over 1 over n plus 1 is monotonic. Please verify. Okay, by comparing by generating the first few terms. Okay, But you can actually argue it using this way. N plus 1 square over n plus 2. Okay, n plus 2. Is it greater than n square over n plus 1? Or, yeah, probably this is greater than this one. Okay, so if you can prove, if you can prove this inequality, okay, if this inequality tends to be true for all n, okay, then your sequence is actually increasing. Okay. But if actually is if it's actually the other way around, baka kasi instead of greater than, baka less than siya. Okay. So it's actually decreasing. But here we verify that it is increasing. Okay. But the thing is that this term has no upper bound. Okay. Because when n is 1, that's the minimum value of n. This is 1/2. So this might have a lower bound of 1/2. That's the minimum value of n. Okay, but as you go along, from n equals 1/2, this one is actually increasing. And in fact, if you find the limit of n squared over n plus 1 as n approaches infinity, this actually grows very large. So therefore, there is no upper bound here. So therefore, this is an unbounded sequence. Okay. We call this as a sequence having no upper bound as an unbounded sequence. So monotonic siya, okay, but not bounded. So therefore, this is a divergent sequence. Okay. So the sequence Cn is equals -1 raised to n is bounded, because again, as I told you earlier, this sequence is both it just oscillates between -1 and +1. So bounded siya. The lower bound is -1, the upper bound is +1. Okay. But it is not monotonic because it increases, then decreases, then increases, then decreases. Okay, so it is not monotonic. So this is a divergent sequence according to theorem 5. Okay. Although there is also a harm in concluding, again, there is also a harm that can be inadvertently be done when you use theorem 5 exclusively. Okay. As in the case of this one, okay, which we have already determined that is convergent. Okay. But this is convergent, but this is not monotonic. Okay. So you may be use theorem 5 to argue a sequence if it is convergent. Okay. But don't use this to say that a sequence is divergent. Okay, that's what the theorem 5 is all about. Use theorem 5 to argue a sequence that is the convergence of the sequence, but don't use it to argue that the sequence is divergent just because it is not bounded or it is monotonic. I was just able to say here that this is not convergent because obviously the sequence is just oscillating. So therefore, from there, we can already say that this is divergent. Also, in this one, in this case, okay. But I am not using theorem 5 to say to argue that these two are divergent. Okay. I am using the argument that the general behavior of this, okay, is what makes them divergent, not theorem 5. Okay. As you can see in example 9, only letter A was able to say that it is convergent because it satisfied the requirements of theorem 5, that it is bounded and monotonic. That is why it was able to make a case that the sequence is convergent. But as you can see, for letter B and letter C, there is no conclusion. Okay, there is no conclusion based on theorem 5 because it doesn't satisfy the requirements of theorem 5 for the sequence to be convergent. And we don't argue, again, I did not argue, okay, for sequence Bn and Cn to be divergent because of theorem 5. I argued for them to be divergent because of their general behavior. Okay, so I hope that is clear to you. Okay. Now, incidentally, both sequences Bn and Cn are divergent. Okay. However, ito yung sinasabi ko. Okay. We will not conclude a sequence divergence if it is not both monotonic nor unbounded. We will not conclude a sequence divergence if it is not both monotonic nor bounded. Okay. Indeed, there are sequences that are bounded, okay, not monotonic, but is convergent. Okay. This sequence is generally not monotonic. Okay. Uh, but not monotonic because tawag ito. Uh, for example, from here to here, it is decreasing. This is decreasing. But take note that this increase. So that is not monotonic. Okay. But as you can see, the general behavior of the sequence is actually going towards 0. So therefore, if you actually evaluate the limit of e raised to negative n over 2, cosine of pi n over 3 as n approaches infinity, you may be able to say that that becomes 0 eventually. So that's a convergent sequence. Okay. But it is not monotonic. Okay. So we won't be able to argue using theorem 5 that this sequence is convergent just because it is not monotonic. Okay. So that that finishes up our discussion on sequences. Okay. So we will proceed with the next lesson on series.